models, right? So sort of the next level abstraction you can keep in mind is your model class. So let's just rattle off some models that we've been studying so far.
KNN.
Yeah, KNN. Yeah, what else? Someone else?
Trees.
Yeah, trees, great.
Linear model.
Yeah, linear models. And we have two types of linear models, right? So we have linear regression and linear classification, which we also refer to as logistic regression. So logistic and just linear regression. I think that's most of what we've covered so far. So this is probably what's on the midterm as well. Okay. So in general, you can have other choices of models too, right? So if you think your data is linear, like it's coming from some physics or chemistry experiment, and you want to model a linear relationship, then you should choose a linear model. And this is something we'll discuss a bit more soon. Okay. So the next layer is the optimization problem. So this is where we sort of define like what our objective is. And we mentioned last class that there's entire classes of problems that are easy to solve. So convex problems are easy to solve, and there's entire courses on trying to formulate a problem and its constraints into a convex formulation. So convex problems are easy to solve. And here we've primarily focused on like two of the most canonical things that most machine learning folks would know about. So in the case of linear regression, we focused on the objective of mean squared error minimization. And for logistic regression, we have this cross entropy loss, right? Okay. And one thing, I guess, to keep in mind is that each layer of abstraction sort of depends on the layers above it. So your choice of optimization problem is going to depend on your model and also on your type of data. And finally, we have optimization algorithms. So given your problem, your model, and your data, we have different algorithms for trying to solve. So what's the main, or what are two types of algorithms we've learned for solving problems so far? Yep.
Gradient descent.
Mm-hmm. Yep. Sorry? Yeah, you could use Atom as well. So Atom is sort of a variant of gradient descent, or you can consider momentum, which I think we mentioned briefly in lecture and in tutorial. And then there's more sophisticated methods like Atom.
And direct computation.
Yeah, we could also do directly solve equations potentially, right? So directly solve. So we saw that this is possible in the case of linear regression, because there's a closed form solution where we can directly plug stuff into the equation and get our answer out. And in the case of convex problems in general, you have this way of solving the problem directly. So in general, when you were discussing a new topic in this course, it could be useful to think about which level of abstraction we're in currently. And within each, we can go into like varying depths of how detailed we are, right? So like gradient descent, we sort of actually discussed 3 possible ways you can do gradient descent. So you can go full data set. You can and this is usually just called vanilla or plain gradient descent. You can do n equals 1, so this is called stochastic gradient descent usually. And then you can also have a mini batch size, maybe n equals b, which is somewhere in between full and stochastic gradient descent. And you should try to understand the trade-offs between these different choices. So for n equals 1, we'll refer to that as stochastic gradient descent, but when you're reading about other people doing experiments, like on the internet, people often refer to mini batch as also stochastic gradient descent. Yeah, question?
Why is it called logistic regression when you use it for classification?
Yeah, this was pretty confusing when I learned, but people just call it logistic regression. There's no good reason. We should really call it logistic classification. Yeah, go ahead.
Can you go over a Socratic gradient descent again?
Can go over stochastic gradient descent? Yeah. So the n equals 1 case or the n equals b case?
You can do one.
Yeah, so n equals 1 is, what we do is for each data point, we compute the gradient of the loss function with respect to that data point, and then we update our parameters using that gradient.
So it's on every point.
Yeah, so the way this works is if our data set is n points. So this lecture, I'm happy to make it sort of a hybrid review session as well because the midterm's next week and we're a little bit ahead. So the way this works is we're going to iterate through all the points. So for I equals 1, 2, all the way to n. And this is usually shuffled. What we're going to do is we're going to update our parameters. So let's call that wk maybe. So the update is going to be wk plus 1 is equal to wk minus the learning rate times the gradient with respect to xi, yi, wk. So that's the gradient descent algorithm. So I guess one term you often see used is when you go through your entire data set once, we call that one epoch. In general, when you're training something like a neural network, you probably want to go through your data maybe 100 times. So we'll say we do 100 epochs of training. And another term is each time we update the parameters, we call that an update or an iteration. Yeah.
So I'm confused on so I get why you're doing this, but isn't this going over the full data set? So what's the difference between full data set and reproduce something?
Yeah, so this is different because we're actually making big N number of updates. So if you're going through so this is stochastic gradient descent, right? If we consider full batch gradient descent, what we're doing here is instead of doing updating by one single point at a time, we're going to estimate our gradient by taking the average across all the points we have and then making one update. So the way that would work is we have wk plus 1 equals wk. We still have the learning rate, it's unchanged, except now we have a summation from I equals 1 to n Does that make sense? So each time we update WK, we're getting a lot, like our direction is more accurate. Because we're estimating the gradient using all the points rather than just a single point or a few points. But this ends up also being like more expensive, right? Like to compute one update where we have to use all the points. So for the same amount of compute, we have fewer updates. Yeah, follow.
Follow-up, shouldn't there be a 1 over n in front of the gradient?
Yeah, I guess in general, you can hide that factor into the learning rate itself, or you can also, in general, it's probably best just to put this 1 over n in, just so the learning rate doesn't depend on the size of it.
And so it's like the bigger the patch, the less update you're doing, and you're taking the average. So like on stochastic, because you're doing once per time, technically the batch is just 1, so you're just taking like the average of itself.
Yeah, exactly. So if before we start our experiment, we know that we can look at 100,000 data points at most, and our data set is 10,000 points, then if you're doing full batch gradient descent, that means we only make 10 total gradient updates and we've exhausted our compute. But if you use stochastic gradient descent, you can make 100,000 updates to your weight vector. In general, the optimal parameter probably depends on your data set, but it's probably somewhere between 1 and the full batch size. Okay. Any other questions? Yeah, Alan?
In both of these cases, you need your entire data set to be relatively uniform, because otherwise it's not going to learn anything.
Yes, yeah, that's an implicit assumption we're making, yeah, but there is some underlying pattern that we're trying to learn. Yeah. Okay. So I guess to be a bit more concrete, we can actually think a little bit more about the homework 1 question we had. So in homework 1, we sort of had this problem where we're trying to classify whether headlines are real or fake, right? And some people mentioned they wanted some more discussion on natural language processing, so we can do a bit of discussion here. So natural language processing is in general dealing with words and figuring out how we can extract meaning from various sentences. And in the case of headlines, we chose a type of model that's often referred to as a bag of words model. And the way the bag of words model works is for each feature, so each data point in our data set, which was a headline, we're going to decompose it into a big array where each index corresponds to a word. And there's a 1 or a bigger number if that word exists, depending on how many times that word shows up, and then generally zeros, because the vast majority of words won't show up. So this is a sparse matrix. And you should see that when you print it out, if you were printing out your data points, you would notice that sometimes they represent it in terms of a sparse representation where they don't actually list out all the zeros. They just show which entries are not 0. So what would be a potential disadvantage of using a bag of words model? Like, what are we losing? Cool. Yeah. There.
Word order?
Yeah, we're losing word order, right? So that's actually really important because as you see with like ChatGPT and other, yeah, did you have something?
Do we also just have to deal with like high dimensionality?
We do deal with high dimensionality as well. Yeah, that's a good point. So this is sort of the first naive approach that you generally try when working with NLP, but then later on we might allude to how RNNs or some more sophisticated methods work. But in general, you can sort of see how this is throwing away a bunch of information, right? Like word order generally matters. Like if we have something that says, this movie was great, if you added an additional word like not into here, that's going to change our classification drastically, right? Like if we're trying to do sentiment analysis, which is figuring out whether or not a given sentence is positive or neutral or negative, then the presence of the word not has a really dramatic effect. And word order is something that's really important for helping us understand that. Okay, and if you wanted to look a bit more on this topic, there is something called CAR RNN. It's actually made by a former U of T student, Andre Kaparthi, and you can Google that and try to see what's going on there. So the idea is that rather than focusing on individual words, he designs a model that looks at each character, one character at a time, and tries to predict the next character. So in general, GPT is going to work with words and predict the next word. You can also actually get surprisingly realistic text as of 10 years ago just by looking at characters. But now we've seen that if you have really big models and a lot of data, the word level way generally works well. Okay. Yeah, I guess in general, I'll allude to some things that are sort of beyond the scope of class, but if you're interested, you can always look at it more. Oh, yeah. Yeah, I guess we primarily just use count vectorizer, right, in the first homework. In general, like when you're doing NLP with neural networks, what people do is rather than learning a count-based vectorizer, you learn a vector representation for each word. And that's learned to minimize your loss. So it has like no natural meaning, it's more just something that minimizes your function. Okay, cool. Any questions on any of this? This sort of ties in with lecture in when we're talking about Lee's set of slides here. So I'll just go through Lee's slides again. In general, we have this idea that we're trying to learn this function that maps from our input to our outputs, and we call this our hypothesis. And then the hypothesis space is sort of all sets of functions that your model can represent. So for linear regression, we can potentially represent all linear models that are linear combinations of the features in n-dimensional space, right? And in general, the goal of the machine learning algorithm is to find a good hypothesis F. And this concept that we've sort of been alluding to, it's something called the inductive bias. Is it saying whether or not our hypothesis class will prefer some hypotheses over others? So this is sort of a vague definition. In general, it means that when we're trying to design a new machine learning algorithm, we want to take our data into account. So you should think about our layers of abstraction, right? If you're dealing with natural language processing, you sort of want to take a model that's good at dealing with text and also the sequential dependencies between text. So inductive bias is the idea that your algorithm should reflect the data that you're trying to capture, and it's sort of the practitioner's job to identify what sort of algorithm you want to use. One classical example is if you're dealing with images, the traditional approach is to use something called a convolutional neural network, which is good at learning the filters and other types of features that are needed for dealing with images. And as we saw with text, there's something known as a recurrent neural network. And then sort of one of the big breakthroughs in the past 5 years is there's this general architecture called the transformer, which is really great at dealing with sequences of data points. the idea underlying all this is something known as the no free lunch theorem, which says that there's no algorithm that's guaranteed to be better than all other algorithms. It really depends on your data set. So you can't just say, let's pick one algorithm and stick with it forever. It depends on the type of data you have. And then sort of two ways we can distinguish between different algorithms is there's algorithms that are known as parametric algorithms, where we go in with a set of parameters, and the way these sort of algorithms work is we have our training set, and then we have some parameters that we want to learn. We take in the training set parameters, do some optimization, and then we end up with like W final. So I think the best way to conceptualize this is like for linear regression or logistic regression, we have a set of weights that we want to learn. Neural networks also have a bunch of weights. And then our training set tells us how we should update the weights in order to best classify or do regression. So after we have our final weights, we usually just evaluate the validation. There's also the idea that some algorithms actually don't have parameters. The way they behave is dependent on the data set. And the two examples we've seen are k-nearest neighbors and decision trees. Okay. Let's actually go back and fill out this chart. So we sort of started doing this last time where we were contrasting linear classifiers and k-nearest neighbors. So one thing we just learned now is linear classifiers are going to be parametric, while k-nearest neighbors is a non-parametric method. So yeah, for each of these trade-offs, which I sort of listed off, let's try to figure out how both of these algorithms behave. Yeah.
Quick question. Is there any link between like parametric and non-parametric and features? Do all like data sets require feature extractions?
So the features are usually just the data points we're given, right? So I guess perhaps some non-parametric methods are more dependent on how features are scaled. Like we saw in nearest neighbors, the scale really matters potentially. Yeah. Okay. All right, so yeah, question or comment?
Would you say parameters in a parametric one would be hyperparameters, or would they be like something that we train on?
Yeah, we generally refer to parameters as things we train on that we can just take and use at test time. So I guess in the case of linear models, we have these weights that represent how we should map the inputs to the outputs.
And then the weights are changing through every iteration of update.
Yeah, exactly. Okay, cool. So for decision boundaries, what can we say about the decision boundaries of linear classifiers versus k-nearest neighbors? Yeah.
Linear classifiers have simpler decision boundaries than k-nearest neighbors?
Yeah, well, they're generally simpler. They're going to be linear, right? So even though it's called logistic regression, even for logistic regression, even though logistic might not sound like linear, in the end, we're just learning a linear decision boundary as well. We could potentially use higher dimensional features, which project to a lower dimensional subspace. They become nonlinear, but in general, by default, logistic regression is going to be linear. While k-nearest neighbors, especially for small k, it's going to be more complicated, right? So you can think back to the pictures we drew before. Based on how the data points behave, k-nearest neighbors is going to end up with a lot more complicated decision boundary. So sensitivity to scale, we sort of just covered. Linear classifiers are going to be less sensitive. Well, k-nearest neighbors is more sensitive usually. Why would we say that linear classifiers are less sensitive to scale? Yep.
We just affect the coefficient for one of the ratios determining, and we like change the actual shape or like the decision factors of each figure.
Yeah, I think what you're saying is like we can adjust the coefficients according to the size of the scale. So if we scaled everything down by a factor of 100, we could get the exact same decision boundary by just scaling the weight corresponding to that feature by 100, right? So essentially we can scale our weights and we don't need to worry about normalizing. Whereas k-nearest neighbors is going to be more sensitive because we have this concept of a distance metric. Right? We usually take this to be the L2 distance between points. That's how we measure what the closest neighbors are. And that's really sensitive to the scaling. So that's why I usually normalize before you do k-nearest neighbors, because unless you have reason to believe one feature matters a lot more than other ones, you want to normalize. In terms of the number of parameters, how many parameters does a logistic regression generally have? Yeah.
Number of features plus 1.
Yeah, it's going to be features plus 1. Yeah, right. Because for each of the features, we learn a weight associated with that feature, and then we also have this bias term. Whereas k-nearest neighbors has no features at all. Has no parameters at all. And yeah, sorry, let's make a clearer X. So that means there's also no training time. Whereas there is training time for logistic regression, we have to do gradient descent. But the main advantage of having a parametric approach is at test time, it's relatively cheap to use. Whereas for k-nearest neighbors, it's pretty expensive at test time. So that's sort of some of the differences you can conceptualize, and perhaps the parametric versus non-parametric distinction can help think about the algorithms more. Yeah.
So when we talk about test time, right? Let's say like I want to like add new data points and I want to test how that works, or rather I want to have like real world predictions. That will be testing, right? So let's say like for example, if I'm using ChatGPT every day, like 10 times a day, then if ChatGPT was non-parametric, that would take me a long time to like ask it questions. But if it's parametric, then it will be quick to answer my question.
Yeah, exactly.
Like, can I think of it that way?
You can think of it that way, yeah. So like if ChatGPT was doing a nearest neighbors approach, that would take like on the order of days probably to get a response, because it has to search through its entire library of other people's questions and responses and then match like your response to whatever is closest to it. But instead it's definitely doing some sort of parametric approach where it learns a function that takes in your input and like tries to generate a good answer. So I guess like if you really want to deploy at scale nearest neighbors, probably it doesn't make sense if you have billions or trillions of data points. Well, we can actually do a little bit of coding in the second half of lecture, just because I know some people like seeing things written out in code as well. Okay. Yeah. Yeah, so this is highlighting that k nearest neighbors can potentially learn nonlinear decision boundaries. Okay, there's one other thing we have to talk about from this lecture, and then we have a few slides for the next week, which is gradient checking. So when you're implementing an algorithm, for example, on your homework or on some future project, you often want to make sure your gradient is done correctly if you're trying to implement things by hand. And the way we do that is we just go back to the definition of what a gradient actually is, and we can estimate it numerically by plugging in the definition. So if we're looking at the gradient with respect to a parameter, let's call it xi, the definition of the gradient is what the slope essentially is at this specific point as you zoom in on this specific point. So if you write it out as an algebraic expression, we define it to be the difference of xi plus h minus, I guess we want the two-sided definition first because it's a more general definition. So we zoom in on xi plus h and compare it to the difference in function values at xi minus h. And then as you make h smaller and smaller, that's what the gradient actually captures. So through calculus class, we've learned simplifications, like actual rules for how you go about calculating derivatives or gradients quickly. But this is sort of the true numerical definition that we start from. So the point is, even if you have like a linear function, like for your linear classification example, you have this f function, you can estimate the gradient using this method as well. So we don't have to go through the algebraic exercise. For each point, we can actually go through this approach, like increase it by 0.01 or something, and then measure how much the function changes. And that's the numerical estimate of the gradient. But of course, you don't want to do that, because if you have a million parameters, that's going to take a very long time versus computing it with a vectorized form. But this is what you should do when you're trying to check the value of your gradient. So in pictures, the way to interpret the gradient is if we're trying to look for the gradient at this term f of x, what we can do is we can look at how much the function changes. So f of x plus h, compare it to the function value itself, and then we divide. It's like rise over run, right? So we want to compute this expression. So the goal is to find what the limit approach is. As you make h smaller and smaller, you can use this one-sided definition, which works, or in general, the two-sided definition probably gives you a slightly better approximation. So you look at both how the function changes as you increase it and as you decrease the value you're considering. So generally, if you're not sure your code is working correctly, the way to check this is you pick some small randomly chosen inputs. You have to use double precision ideally, so you have more floating point accuracy. And then you plug in small values of h and check whether the gradient you compute using the algebraic formulas that we derived matches the gradient you estimate numerically. So if the amount of the error is really small, then that generally means we're on the right track. Okay. And this is important to keep in mind because sometimes machine learning algorithms still work, just not really well, even if the gradient is wrong. So sometimes you'll get performance that looks like it's converging a little bit, but not actually totally converging. So to rule out one possible source of error, you might want to consider implementing gradients numerically. Okay. Any questions on gradient checking? All right, so we're gonna cover the first three things here. And then the rest of the time we'll focus on midterm review. So I think the first three parts will take 10, 15 minutes maybe, and then we'll start on neural networks, the next lecture we have. So primarily we've been just only focusing on the linear, on the logistic regression case with two different classes. But in general, we can have much more than just two classes, right? So this is the MNIST data set. I think these are handwritten digits, so you might be considering this sort of application if you're trying to recognize the digits on a handwritten check, like you want to be a bank writing some automatic check deposit system. And these are some of the hardest examples on MNIST, I think. So these are examples where it's potentially really ambiguous, even for a human, what some of these digits actually are. So the ones in the green boxes might be 2s, but it's like a pretty random set of numbers. We can also just do image classification more generally. So these set of examples are different images from various different classes, and the goal is to identify what class the image belongs to. There are many examples of classification data sets. There's a data set known as Fashion MNIST, which people sort of designed to be identical to MNIST in terms of the sizes of the images, but instead of classifying digits, you're classifying what fashion item each of the images corresponds to. And then from Canada, actually, we developed two data sets that are frequently used for benchmarking various algorithms. So there's CFAR10 and CFAR100, which are data sets of natural images, and the goal is to classify what images they are. And then ImageNet is sort of the big 1000 class data set where a lot of progress has been made in recent years. So those are just some examples. I think image classification is probably a running example you can keep in the back of your mind. So the idea here is rather than just having two different classes, we now have k different classes. So we encode our targets usually as one-hot vectors, which means they're going to be entirely zeros, except there's going to be a 1 corresponding to the correct class. And our targets are going to be in r to the k. So if we have r to the k targets, that means our output space is now k-dimensional. And let's say our input matrix is still n by d. If we're trying to learn a linear classifier, what should the matrix in the middle be? Like, what's the dimension of the matrix in the middle? Yeah, it's going to be roughly d by k. Good. Or potentially d by k plus 1 if we have a bias. And this is sort of different from logistic regression, right? Because logistic regression, we only have one single output. Since we have two classes, we can use this one output to determine whether or not we're in class 1 or class 2. But if you're dealing with k classes, we don't have this sort of trick anymore, so we're going to predict all k classes, like predict targets for every k value. So more concretely, we're writing out this in vectorized form. Our predictions are going to be of the form z equals wx plus b. And let's just write this out. So our data matrix is n by d. And this should, in general, the W matrix, in general, when we're doing operations, it should be output by input dimensions. So I think if we write out our matrix in this way, we actually want, sorry, let's focus on one single data point at a time, because I think this example works better that way. So let's restart. So W is K by D. And then we have our input feature vector, so X. X is going to be D by 1. So sometimes when you're dealing with matrices or vectors, you have to play around with the shapes to make sure that they match up correctly. When you're doing this in NumPy, you can do dot T, which stands for dot transpose. So if you have some vector X, if you do X dot transpose, it's going to transpose the matrix. So useful to keep in mind. And after we multiply this WX matrix, we're going to also add B, which is a K by 1 vector. So this is a K by 1 plus a K by 1, which gives us a K by 1. There's a K by 1 dimensional output of our function. Yeah.
Can we not put B in the matrix?
Yeah, we can definitely put B in the W matrix. So that corresponds to adding an additional row of all ones. Yeah.
And in this case, K would be the parameters and D would be all the different data points.
Yeah. In this case, K.
For the W.
Yeah. No, K is the number of classes we have. Yeah. And then D is our number of features. So in general, this can be a little bit confusing because sometimes people have different row versus column conventions. The important thing to keep in mind is you want to keep track of which dimensions correspond to the features and make sure you're like multiplying them correctly so that in the end you have essentially one weight vector corresponding to each class you're trying to predict. And we're just writing this out in matrix form, so when you do the matrix multiply, you're generating a prediction for each of the potential classes. Okay. So the way we interpret this K by 1 dimensional vector is we treat Z sub K as how much the model prefers a kth prediction. So rather than just having a simple logistic cross-entropy loss, what we're doing instead now is we're saying we're going to take the argmax, so whichever prediction is the maximum among our prediction vector, and we're going to take that as our prediction instead. I'll talk about how it relates to the K equals 2 case in a little bit. But this argmax function is sort of similar to the 0, 1 loss function in that this function itself is not easily differentiable, right? So we're going to apply the same fix we had before to make things differentiable. We're going to use a softer version of the maximum instead. And this is actually just called the softmax function. It's a really natural function to define if you're trying to convert something from real numbers into a probability distribution, because whenever you take the exponent of something, you get a non-negative number, right? So what we're going to do is we're going to raise everything to by the power of e. So in code, you can do mp.exp. And what this is doing is if we have our potential z values, let's say -2, 0, 3, and so on, we're going to take the exponent of each of these values. and then we normalize. So this is sort of a softer version of the maximum function, because if you have a really big value, it's going to dominate all the other values, and it's saying we're really confident in that particular class. Similar to logistic regression, we call these ZKs the logits, and then we can interpret the outputs of the softmax. So these Ys, they're the probabilities. And the reason it's called a softmax again is because if one ZK is much larger than the others, then it behaves essentially like an argmax. Okay, let's actually look at the case for n equals 2 a bit more concretely now, just to check that this mostly agrees with what we've been doing before. So for n equals 2, if we're taking this new approach instead, what we're going to do is we're going to generate a z1, which is w1 times x. So this is the first row of our feature matrix. And then we also have a z2, which is w2 times x, right? And then we can look at the softmax function. So let's say we're looking at y1, which we define to be e to the z1 over e to the z1 plus e to the z2. If we substitute in our definitions, we have e to the w1x over e to the w1x plus e to the w2x. How can we simplify this expression further? Remember, like for a logistic regression, we have this function that looks something like 1 over 1 plus e to the minus u, right? So this is the logistic cost function that we previously derived. So in order to simplify things, because we're dealing with exponents, you can actually just divide by the quantity itself, right? So what we're going to do here is we're going to divide everything by e to the w1x. So that's going to leave us with a 1 in the numerator and a 1 here, plus e to the w2x minus w1x. So you can simplify this to e to the w2 minus w1x. So what this is essentially saying is we could also have done logistic regression by learning two different matrices corresponding to how much we think each feature corresponds to a given class. But instead, in logistic regression, we're like secretly learning the difference, like how much we prefer one class over another in this form here. So logistic regression, we just learn a single matrix W. But if you're dealing with a general multi-class case, you can also just approach it this way, where you're learning a matrix, learning a vector associated with each of the classes. Any questions? Yeah.
What is an activation function?
Oh yeah, so an activation function is applied to turn some distribution into another distribution. I guess the main activation function we've learned so far is a sigmoid activation function, which scales everything to be between 0 and 1. And that's something we'll see more later on. Okay, let's look at how the loss behaves now for logistic regression. For this new cross-entropy loss. So what we're going to do now is we're going to define this objective that looks like the summation of these terms. what you should instead, I guess, picture is like we had this loss function from the previous class, which looks like this. It should actually hit 0 at 0, right? And then there's a 1 here. And what this loss function that we did from before was doing is it's saying if we make a correct prediction, the loss is 0. But if we make a wrong prediction, the loss scales and it becomes bigger and bigger the more wrong we are. So if we predict a probability of 0.99, the penalty is a lot bigger than if we predict a penalty of, if we predicted 0.8 instead. So the loss function before, by using the log, it's penalizing how far wrong we are in accordance like the confidence of the current model. And this is sort of just generalizing what we had before to this multi-class case. So it's saying for whatever the ground truth label is, we're going to apply this log loss function and then just sum up our losses. So as before, you can also, for numerical stability reasons, combine both the softmax and this cross-entropy loss in one single term. There's also a question from last time about whether cross-entropy has another meaning. So in general, there's actually an information theory meaning from cross-entropy. We aren't going to go into the details here, but it's sort of a way you can measure distances between two different distributions, and it's a natural way in terms of bits you can think about information theory. So you can Google cross-entropy if you want to look at that interpretation more. Yeah. I think we can take a break for now because it's been a lot of talking. Let's resume at 12:20.